Okay, so under the water, the molecules are in random arrangements. They're not all in perfect little rows because they've got room to float up and down and be at different levels. And when they do that, they don't always line up perfectly into a nice symmetrical grid of hydrogen bonds. They're moving around. They float past each other. But the ones on the surface are all in a perfect line because, well, they're all in the same place. It's called the surface. They all have to be in the same spot if they're on the surface because the surface is flat. And so when they do that, they can all bond to each other in like straight sideways. And so what it ends up making, as we said, it was sort of like the effect of a trampoline where you have this thing that is like to push through them, you would have to push these molecules apart. And because it's not just in a line, it's like 3 dimensions, well, 2 dimensions. It's in a plane. So there's also one here out in space that's connected to this one and to this one. And so it ends up making this net of hydrogen bonded waters that are all in one plane, and that's what makes the surface tension. All right. We talked about the idea of calories. When you are doing calculations with calories, there will be questions. I gave you one sort of kind of question on that topic if you did the reading quiz the other day. If I give you a mass of water, let me just make sure you understand some of the conversions. A gram of water. How big is it? What's the volume of a gram of water? 1 milliliter. 1 gram of water that's the definition of a milliliter, is a gram of water. So these are the same things. If I tell you that I've got 13 grams of water and I warmed it up 1 degree, how many calories did I use? 13 grams of water that I warm up by 1 degree. 13 calories. It takes 13 calories to warm 13 grams of water up 1 degree.
So 1 calorie per 1 gram of water?
Per 1 degree. So taking 1 gram of water, right here, and increasing it by 1 degree Celsius. Almost nothing in science is in Fahrenheit. The only thing that Fahrenheit makes any sense for, and the other stuff, weather. Weather is not convenient when you're talking Celsius because then you're talking about decimals of degrees. 80 versus 90, it's a reasonable difference that you can imagine. 31.2 versus 33. It's like this little distance numerically, and it just doesn't make much sense. So, but when we say temperature in a living thing ever is going to be Celsius. So all you got to do is figure out how many grams and or milliliters of water is there and how many degrees did you increase it. So 1,000 grams of water increased by 1 degree is 1,000 calories. If I've got 22 milliliters that I increase by...
Wait, so did you say 1 gram increased by 1 degree?
Yeah. So increasing 1 gram of it by 1 degree was 1 calorie. Times 1,000 because we've got 1,000 grams of it. So if you've got 22 milliliters that I increase by 5 degrees... Huh?
110 calories.
Yeah. It's 110. 22 times 5. So it takes 22 to increase it 1 degree. to increase it 5 degrees, you take 22 times 5, and so that's how you figure out how many calories it is. This is a really high number for water.
5 degrees?
No, what I'm saying is the fact that it takes 1 calorie to raise 1 gram, 1 degree Celsius, that's a lot. Iron, would be, like 0.2 calories to increase a gram of it by a degree. It warms up easier. Water,
Is that why it takes so long for something to
yeah, that's why it takes so long for water to boil, but once it boils all at once, instantly. Because most of what you're doing is you have to start, the energy you're putting into it is going to break the hydrogen bonds between the water molecules. Until they're all broken, it won't boil. So it's breaking them, it's breaking them, it's breaking them, but the whole time the water is still only 100 degrees and it's not boiling. It's a lab that they do in, I don't know if they do it anymore, but if you take ice at 0 degrees and you melt it as you heat it up, all of a sudden it will all melt at once, and then as you continue to heat it, it will all turn to steam at once. It's not a gradual thing. So this whole time, I'm heating it, I'm heating it, I'm heating it, it's not getting any hotter. All it's doing is breaking hydrogen bonds until finally it breaks all of the hydrogen bonds between the waters, and now they all turn to steam. And so now the additional heat you're adding is actually going to moving the molecules around. That's temperature. So adding energy to something, if it doesn't make the molecules fly around faster, it's not hotter. You put energy in, but it's still the same temperature. That's the reason why once water is boiling is boiling. That's it. 100 degrees. Boiling water is 100 degrees. You can't make boiling water hotter than 100 degrees, because once it gets to 100 degrees, it breaks all the hydrogen bonds and it turns to steam. If it's in the state of water, it has to be no hotter than 100 degrees, unless you use a pressure cooker, because then the pressure in it holds the water in a liquid state longer, which is why frying something in oil cooks it a lot faster than boiling it, because oil can be 350, 400 degrees, but boiling water can't ever be hotter than 100.
So if you had 5 grams and you were heating by 2, that would be 10,000 calories?
No. 5 grams. We're,
That's only because there was 1,000.
yeah. So what did you say? 20 grams increased by 2 degrees, that's going to be 40 calories. Yeah, that was just the example that was up there. Okay, so just understand that this idea of specific heat is unusually high for water, because unlike other molecules, water molecules are holding on to each other. When you heat up oil, the molecules were never holding on to each other in the first place. They had no attraction for each other. They were all nonpolar. One molecule had no interest in its neighbors, and so every bit of energy you add makes the molecules start moving around faster, and that translates into its temperature. But water, the fact that it clings to itself, you have to break them apart first, which was that idea, remember I said, if you have to take a bunch of balls that are stuck together and you have to beat on them with a stick for a while and break them apart, and then you can, once they're broken apart, then you can make them fly around. Right? So this is, there aren't many things that have a higher specific heat than water. So that means water is better than anything else at sucking up energy. Right? If you, the amount of heat given off on your stove to just get water boiling is enough to, newspaper on fire. Well, that's a lot more energy. There's a lot more heat coming off of that than there is the water. That's because the water can absorb heat. That means on a hot day, the heat from the sun is literally being sucked up by the water, and it's being held in there as energy, but not as heat. And then at night, when it gets cold out, the water, as the molecules start to reform their hydrogen bonds, give off heat, which is why at night the water always feels warmer than the air, and in the daytime the water always feels cooler than the air, because it's actually taking in excess heat during the day and giving it off at night, which is why places that have very little water, like the city or a desert, have huge temperature swings. The desert has enormous temperature swings. It might be 110 in the daytime, and it'll be 52 at night in the middle of the summer, because there's nothing but sand to hold the heat. It heats up fast, and then at night it cools off real fast too, and the heat just radiates back out into space. Okay, so all of these words are, redundant stuff that I said. All right. That's to increase the temperature, was the specific heat. If you want to actually boil it, it's way more. Turning liquid water to water vapor is not 1 calorie per gram. It's 580 calories per gram. That's why when you sweat or if you spray water on yourself and then stand in front of a fan, it cools you down fast, because the water, as it leaves you, as it evaporates away, it's not taking 1 calorie of energy from you. It's taking 580 calories per molecule or per gram of water. That's a lot of heat. Right? So you wetting your skin and then standing in front of a fan, which helps get the water to evaporate faster, it takes a lot of heat from you. It's the reason you sweat. When you sweat, it does not cool you down. Sweating does not cool you down. All you are is hot, covered in hot water. When the water evaporates is when it cools you down. That's why sports clothes are all made to pull moisture away from your skin out to the surface where it will evaporate, as opposed to old school like cotton, like stuff. People don't use cotton for like workout stuff anymore, because all it does is just get sopping wet and heavy, and if it's not evaporating off you, it's not cooling you down. You're just wet and sweaty and hot. So water evaporating is what takes the heat away from you and every other living thing. Not every animal sweats. Dogs can't sweat, they pant. It's the same idea. The water is evaporating from inside of their lungs in their exhaled breath, which it does for you too. It's just you don't they're not miserable when they're doing that. It's basically them panting slightly is the equivalent of you perspiring a little. You're not dying, but that's how you have to cool down. That's how they have to cool down. Okay, so water takes heat from things. But in terms of the importance for the planet and life on it, this is probably the single most important benefit that water has provided. It doesn't sink when it solidifies. Doesn't seem like that would be a big deal, but ice floats. Well, what does that mean? If you have a lake and it is very cold up here, it means that it's trying to pull heat from the water. At some point, you pull enough heat from the water that the water molecules slow down enough to solidify into ice. that ice is now a blanket. It's insulating the rest of the water below it that is not yet cold enough to freeze. Which means the second that the water freezes over, it's being protected from freezing any further. Yes, as winter goes on, I mean, if you're talking about Canada, they can get 2-3 feet of ice on top of a lake. But if it's 15 feet deep, it's still 12 feet of water down there that's not freezing. That means all of the cute little fishies don't turn into fish sickles in the winter. Bodies of water that are deeper around here, 16 inches is the magic number. If a body of water is deeper than 16 inches, it will pretty much never ever freeze below that in this climate. Which means that's how fish and everything else survive the winter. They're still swimming around down there under the ice, and it's not freezing. If ice sank, which is not what it does, the ice would form, and then it would sink to the bottom, and then more water would be exposed, and that would freeze and sink to the bottom. And basically the ice, as it froze and sank, would start to pile up on the bottom, exposing more water, which would freeze and sink, exposing more water, until you just froze it into one solid ice cube. If that happened in the course of a few winters, every body of water on the planet, all of the free water would be solidified. Living things need water in liquid form. You need it to dissolve all the chemicals in your body. Every living thing's chemistry happens in solution. If it's all frozen solid, there's no solutions. Everything would die. In fact, life never would have started because there would have never been water that was available for life to use. Every other liquid does become more dense when you turn it into its solid form, and it would sink to the bottom. Right? When metal hardens, as the stuff goes from liquid metal to solid, the little bits of solidifying metal sink to the bottom until you just end up with one solid chunk of it. Right? So the fact that our water on the planet stays liquid for almost all of the volume of it, except for that thin little layer on top, means that there is basically uninterrupted life. Evolution takes millions of years, tens of thousands of years. If every winter everything died, or almost everything died, life would have to start all over again every year. You wouldn't have millions of years of adaptations building up because the planet wouldn't have been habitable for millions of consecutive years. Maybe every 10 years you'd have a really bad freeze and it would all solidify, and then life would have to start all over again. So the variety of life we see on this planet is because the water didn't freeze. Otherwise, we'd have been stuck on that rope when we had it strung way back over here in the organisms with no nucleus. And that's all we would have ever come up with, because there wouldn't have ever been enough continuous time for anything more interesting to happen.
How come alcohol never freezes?
It does freeze. It doesn't freeze as quickly because alcohol's not polar.
So how long does it take to freeze?
It freezes at -60.
Oh, at a lower temperature.
Yeah, it'll freeze at a lower temperature, right. I mean, oxygen will freeze. Yeah, nitrogen freezes if you get it to -230 degrees Celsius. Liquid nitrogen is -175 degrees Celsius. It'll freeze, but that's what's inside of, Oh, carbon dioxide doesn't have a liquid state. Carbon dioxide is either a solid or it's a gas. When it's a solid, it's dry ice. And then what happens to it is it doesn't melt, it sublimates. Sublimate is it goes from a solid straight to a gas, which means it never there's no such thing as a puddle of carbon dioxide. That's not necessarily true. If you take carbon dioxide in a bottle, which is what they put inside of fire extinguishers, it is a liquid in there. But that's only because they compressed it, not because they froze it. They literally took the gas and squished it until they made it a liquid. Well, that's what's inside of every aerosol can. Like if you've got something where it's like, there's a liquid inside of it, and when it comes out it evaporates, it's because they took, if you've got like paint thinner or something like that, or graffiti remover, you spray it on and it evaporates. Well, that's it because it wants to be a gas, but they compressed it in the can until they squish the molecules so close together they become a liquid. And then when you spray it, it disappears. It's like that canned air that they use to, like, if you use that to like blow the dust off your keyboard, shake it. It's a liquid. But liquid never comes out of it. It's just gas. Same thing with a propane canister that you have on your grill. If you pick it up and slosh it, it's liquid in there. But it never squirts out of the grill. It comes out as a gas because when you let the pressure off, the liquid goes poof, and it puffs back up into a density that is a gas again. Right? But those kind of things usually, like, I guess you could make propane ice. It would just be really, really cold. You got a hand up or no? How the water what? Oh, okay. So, yeah, here. The way water becomes ice, it has to do with how fast the molecules are going. Okay, think about this. Imagine that you are all basically like in a river being washed downstream.
Okay.
And you are trying to grab one another to like hold on to each other. Well, at certain points, if the water is pushing you fast enough, you grab somebody's hand and it just pulls them away from you because you can't hold on with the same strength that the water is pushing you apart. As the water slows down and you're not moving as rapidly, you can get a hold of people and then, everybody could kind of get together. That's what's happening. The molecules in gases are moving so fast they never get a hold of each other. It's like they just fly by each other and they never even get a chance to form a hydrogen bond at all. Water vapor isn't forming any hydrogen bonds. The molecules are moving so fast they never can get a grip on each other. Water molecules are moving fast enough that they temporarily grab their neighbor and then they're pulled away and then they grab a new neighbor and then they're pulled away and then they grab a new neighbor. So they're always holding on to somebody, but it's not the same somebody, which is why water flows. The water molecules stay together because they're holding on to one another, but not the same one another all the time. Some of them get pulled away and they grab onto some different ones until finally you've slowed them down enough that then they can grab one another and just hold on. That's ice. They no longer are able to move around independently. They're all locked in position, and then that's what ice is. So here, gases like ice, they are slow enough that every single one is basically forming its 4 hydrogen bonds that it can theoretically make. Over here, okay, those 2 are hydrogen bonded to them, but this dude and this dude aren't hydrogen bonded to anybody because they were flying by too fast, and then these guys were hydrogen bonded, but these guys weren't. So the difference is here, they're all bonded to everybody. Everybody's locked together in one big grid. Over there, some of them are holding on some of the time. And if this were a picture of gas, it would be nothing but little red and white dots with no hydrogen bonds at all.
How fast does it actually move? Like the water? So
Well, water,
Or like-
literally water molecules are moving as the speed that the water is. So like, if you have water that looks still, like if I took a cup of the water and put the dye in it, like the dye would ever so slowly eventually spread out because the heat from the room is making the water molecules move enough that maybe after a couple of hours, ones from the center will have wandered to the outside and pulled the food coloring with them. So like, I mean, that's why if I put food coloring into it, I don't have to stir it up. Eventually, it will be dispersed in the water, even if I never.
So how fast the dye would move is how fast the...
Pretty much. Well, unless you squirt it in, and then it's moving as fast as you squirted it. But if you like took a drop of it and had it on your finger and just touched it to the surface, yeah, the speed that the dye would disperse through it is about the speed the molecules are moving.
Have you demonstrated?
Sure.
That's not... So if you put it in boiling water, it would be like...
Well, because the bubbles are stirring.
Huh?
Okay, I gotta wait a second because it's all swirling around because I put it in. Come back tomorrow and we'll be done.
Tomorrow?
Yeah, I didn't say it's fast.
He did say it was slow. That's how
I mean, eventually you won't see like concentrated blobs of dye. Eventually the whole thing will just be pale blue. And if you put a camera on it, eventually you just see it fade and fade and fade until it was all uniform. But I mean, I'm not stirring it, but it's moving apart. And part of the reason is, what's part of the reason? Never mind, we haven't done this yet. The dye is diffusing. Things that like to get away from other things of their kind. Basically, molecules are antisocial. They don't clump together, they want space. Where I put the dye, I put all of the ink in one place. Those molecules want to get away from one another, and they're moving apart. But they're only moving apart at the speed that the water molecules get out of the way. And so basically it is like blending in there at the speed the water molecules are moving. But it's slow. Okay. Next. Hydration shells. Okay. Water is the solvent of life. There's a reason why we are so excited when we find water on other planets. They just recently found liquid water on Mars. Okay, it's more like mildly damp dirt. But technically, damp dirt is wet with liquid water. There's no streams, but they have found like basically damp spots on the surface, which means there is liquid water. Which means that as far as we understand it, life can exist. We have no concept of what life would be if it used something different than water. That's one of the things, like Europa is one of the moons of Saturn that they've recently discovered has, or no, Titan, I'm sorry, Titan has oceans on it of liquid methane. Methane is the gas that comes out of like your stove or the Bunsen burners in here. It's so cold on Titan because of how far it is from the sun that it rains methane. It has the same like concepts as water. There's lakes, there's shorelines. The water, like the methane, evaporates when it's warm, and then when it gets cold, it rains methane. But methane is non-polar. I mean, methane is that's methane. It's non-polar. It's uniform. It's symmetrical. So that means none of the stuff water does would happen the same way. You'd need to reinvent the entire chemistry of life to come up with some way that a living thing could exist with methane as its solvent. Everything would have to be based on things that were non-polar. We're all based on things that are polar. Like nothing we know of could live there, but that doesn't mean that it isn't. Now there is another planet, or another moon, which was Europa, which is another moon of Saturn, that they have discovered an extremely deep liquid water ocean underneath the ice cap. I'm sorry, it's Enceladus. Enceladus? I can't remember which. Encel something. It actually, they discovered it because they found actual like geysers of frozen like frost squirting out of these little volcanic vents, and it was like water squirting out and instantly freezing in the cold of space. But it has a liquid water ocean underneath the ice. The reason it stays so warm, like the only reason it stays warm out that far, is that it's so close to Saturn that the gravity of Saturn is like distorting it. So as it gets close to Saturn, it's pulled this way, and then when it moves away, it goes, and so it basically, it going like this is like, taking dough and kneading it, and it warms it up as you squeeze it, and it's called gravitational heating. It's actually like wiggling like that, and the friction like of the actual rock is warming it up enough to keep the oceans liquid. That's the best place that we found in the solar system so far. There's a reasonable chance that there might be life there, because if it's been a liquid water environment like that for that long, we know it's liquid underneath because ice floats, which means it's been a temperature that's no less than 0 degrees Celsius for millions of years. That's a stable enough environment that some life might happen. Okay, here's the idea of it being a solvent. It's not the universal solvent. It can't dissolve everything. We know it can't dissolve oil. It can't dissolve wax. So it's not the universal solvent. But it can dissolve things that it really has no right to be able to dissolve because of its properties of polarity. Some things dissolve really easily in water. Salt. When you put it in there, the water breaks it apart. The second salt goes into water, it breaks into sodiums and chlorides. It disassociates, it's called. But the reason that the molecules get broken apart is because of this idea of a hydration shell. Here's a picture of something. Say this is a big well, okay, hang on, not something that big. All right, normally things like over here on with the salt, the picture shows there's the chloride surrounded by what? Chloride is negative, right? Which means all of the little positive hydrogens are facing inward, surrounding that chloride, which means that chloride can no longer get to that sodium because that sodium is surrounded by waters with all of their oxygens facing the little positive sodium. Basically, water just kind of goes, it gets in the way, it shoves them apart, and then it stands in between them so that the molecules, like dissolved, means that water has gotten in between individual molecules of whatever the substance is and is keeping them from coming together. When you stir sugar into water, that's what's happening. A molecule of sugar comes off. It is polar. It ends up being surrounded by a bubble of water all over its surface that won't let it come in contact with another sugar molecule, and therefore they don't stick together. So when you stir sugar until it dissolves, that's where it went. It turned into individual molecules that are being held apart by individual molecules of water. So, because water has both, because it's polar, it's got a positive and a negative side, which means you put something that's negative in there, the positive hydrogens can, be attracted to it. Put something that's positive, it'll do that too. Right? So anything that is polar, one of the two sides of a water molecule will be attracted to it and basically completely cover the surface of it in a layer of water molecules that are clinging onto it and making a buffer where two molecules of sugar can't touch anymore. There's literally two water molecules in between. One stuck to this half, one stuck to this molecule, and they can't touch, which means they can't bond, which means they are not a solid anymore. They're broken into bits that are in solution. No, this is polar. Oh, this would be non-polar. Right, because it's got like hydrogens. That's methane. That's what we said was like the gas that comes out of your stove if you have like a gas stove. So this hydration shell is literally this layer of water surrounding the molecule, holding it away from neighboring molecules of that stuff. Water. So like right here, like I don't know if you can tell. Like so right there, if we draw sodium chloride.
Can you repeat what you said? It's a layer of water that holds water.
Okay. It's a layer of water holding individual molecules of the solute. Whatever solute is the whatever you are dissolving. The water's the solvent, the stuff you dissolve in it is the solute. So over here, here's salt. Sodium chloride, sodium chloride, sodium chloride, sodium chloride. They're sticking to each other because they can touch one another. And they're positive and negative charges, so they're attracted to each other. Here's salt that's been dissolved. There's a chloride. It can no longer touch this sodium because there's a bubble of water molecules clinging all over the chloride. There's another one clinging all over here. So when these two try and touch, these two water molecules are physically in the way, keeping them from ever coming together. That's what dissolved is. And because of the polarity of water, it can dissolve everything except just straight non-polar stuff. Like oil, the water has nothing to do with it. It can't cling to any part of it, which is why you put like oil in water, and as the oil floats together, it clings into it sort of like small droplets float together and they fuse into a bigger and bigger blob, right? Because the water can't get between them. The water's not interacting with it at all. Yeah, done.
So the red bubble things
Or waters.
are the hydration. Is that the hydration?
Yes. And I don't. Here. Not sure if you can see it well enough. So here is one of the sodiums, and
That's what I think.
There, does that help? Okay, so here's chloride, it's negative. The little hydrogens, right, water's ears, are positive. So that's the way that the water is surrounding the chloride, with the hydrogens facing in and the oxygens out. Sodium is positive. It's got the negative water facing in and the hydrogens facing out. But if these two try to float together, these two water molecules are simply going to bump into each other, and those will never touch. Right? They're forming basically it's like taking two things and wrapping them in bubble wrap. They can't touch. Like the bubble wrap will touch, but that's not the two things in it. The sodium and the chloride will never touch each other because the water is acting like layers of bubble wrap around them, holding them away from each other. Well, that works for little stuff. It can even work for big stuff as long as some part of the molecule is polar. Something like proteins are too big to reasonably dissolve. Like the molecules are so, if this is one molecule of protein, it's so much bigger than the water, you should see chunks of it floating around, except that because it gets completely covered in waters, even two giant molecules of protein won't stick together. Same thing with starch. Right? There's a reason why you can dissolve starch in water. Starch is a giant molecule. It won't dissolve if you put it into any other liquid except for water, because water has the only thing that's going to be able to surround each starch molecule in its own little bubble.
Does that benefit life?
Does that quality benefit life on Earth?
Does what?
Does that quality, like the hydrogen show?
The hydration shell is the only reason you have chemistry in your body. The reason that your blood and your cells, like, think of it this way. All right, so here's our little sodiums and chlorides. They're not stuck together anymore, which means when the water moves around, they move around. If this chloride is going to end up connecting to a carbon over here, it's got to go over there. This chloride can physically float in the moving water over to here. If you look, our water is kind of all uniform now. Because the molecules are separated from each other, they can move. Which means this chloride can get close enough to this one to have a reaction and have them stick together. The water doesn't do anything magic, with the exception of maybe like when it does actually, it doesn't really do anything magic. It just gets in the way and gets out of the way. The water is just the way that these molecules move. There's a reason why almost every chemical reaction happens in solution. It's the only way the molecules can move around. If you're going to take one molecule and change it, you've got to take some atoms off and put different atoms on. And if they can't move, they can't do that. It's only because they're floating that the pieces can move around and come in contact with each other the right way. Right? So the water is just the way that the molecules move around so that they do come in contact with each other. I don't need you to have like a super deep understanding of this. We'll like, you know, we don't need stereochemistry or anything here. But, yeah. All right. And all right. If you sweat, there is salt in there. The sodium and the chloride are being held apart until the water evaporates, and then what? you get that crusty, salty feeling on your skin, because now when the water evaporates, those chlorides and sodiums can come back together and reform a crystal of sodium chloride that is now a solid again, right? Especially if you get like salt water on you, like ocean water. When it dries, it leaves like salt crust behind, right? That's why. It was in solution when it was wet, but it's not once the water's gone. Yeah, done.
Okay. So like 5 minutes before this class is over, can you like tell us what
All of this.
So it's just this whole text here. Should we just study from here?
Yeah, just study from there.
Is that sarcastic?
No.
How many questions?
No, I'm sorry. It wasn't sarcastic. All right. Let me, look, we got like 20 minutes left.
Can you outline all those important things?
Yep, if I can get through this.
Okay.
Yes. All right. Last couple things. When you make a solution of something, you need to know how concentrated that solution is. Concentration of a solution is measured in molarity. Molarity is how many moles per liter of that substance is in there. You need to know what a mole is.
How much is a mole? Is it?
It's a lot.
20.
6 times, yeah, right there. 6.02 times 10 to the 23rd. Here's the deal.
Okay.
Think of a mole like this. How many eggs in a dozen?
12.
How many bricks in a dozen? 12. How many cars in a dozen? It doesn't matter how big the objects are. A dozen is not a measure of how much it is. Yes, I do realize that 12 cars is more material than 12 eggs, but it's still a dozen of them. A mole is the same thing, so while a dozen equals 12 things, which in scientific notation would be 1.2 times 10 to the first. A mole is 6.02 times 10 to the 23rd. Okay, so that means take 602 and write 21 zeros at the end. That's a mole of something. All right, so yes, that's a mole. Just, what? 21. Because it's 6.02 times 10 to the 23rd, but if you move the decimal to the end of the 02, like, okay, so that's 60.2 times 10 to the 22nd, and that's 602 times 10 to the 21st. So, there is no difference between the concept of a mole and a dozen, except that a mole is a shitload of them. It's a lot, a whole lot. It's a number that you really can't wrap your head around, because you've never in your life dealt with numbers that enormous. A mole of sugar is that many molecules of sugar. Now I do realize that, okay, a mole of sugar is much, much more material than a mole of salt. A mole of sugar is like 92 grams of the stuff. Right? A mole of salt is going to be like 12 grams of the stuff. Right? The way you figure it out, so CO2. You'd need to use a periodic table to look this up. The molecular mass of oxygen is 16. The molecular mass of carbon is 12. So we've got 16 plus 16 plus 12. That's 32, 42, 44. The molecular mass of one molecule of carbon dioxide is 44. So that means 1 mole of the stuff, 1 mole of carbon dioxide is 44 grams. 1 mole of carbon dioxide is 44 grams. 1 mole of sugar is C6H12O6. We don't need to do the math. I think it's 92. It's a lot.
Yeah, it was on the quiz. I got that one.
Okay? But that means a mole of sugar, like mixing up 1 molar sucrose gives you something that is virtually syrup. It's so much sugar. I mean, it's like 2 cups of sugar in a liter of water. It is like so, like, but it's just a way of saying how concentrated is this in terms of the number of molecules. So 1 molar sucrose and 1 molar salt solution. A mole is the number of molecules. If you have if you have a dozen cars, it weighs more than a dozen eggs. Just like a mole of sucrose weighs more than a mole of carbon dioxide, because sucrose is a heavier thing. So the same number of a heavy thing is going to weigh more than that same number of a light thing. Right? But it's a way of figuring out like the concentration. So what is this? This well, there's 72, 12, and let's 16 times 6 is 96. So 108 plus another 72, and 170. So
That's
a mole of sugar of sucrose. I'm sorry, that's a mole of glucose. A mole of sucrose is going to be double that, because sucrose is C12H22O11. So basically, you know, if you figure a sugar packet is a gram. Like, you know, an individual little paper sugar packet is about a gram of sugar. So, you know, to make 1 molar sucrose, I'd need 340 of them. And I need to mix that into a 1 liter bottle, like a regular, you know, like half size. Yeah.
Okay.
So it's most things in your body are like, you know, 0.1 molar. Like most things in your body are very diluted, but it's simply an apples to apples way of comparing how concentrated something is.
How concentrated is the body with water?
The molarity of your blood for, hang on. It's a little decimal.
I thought it'd be a big one.
All right. Okay, so figure that you got to do a conversion here. You've got 90 milligrams per 100 milliliters, which means you've got, was that 9, 0.9 grams per liter. You have 0.9 grams of glucose in a liter of water. 0.9 grams. 1 molar was 240 grams of it, and this is 0.1 gram of it dissolved in a liter of your blood.
So it's like
Or 0.9 grams. So it is like, you know,
0.01.
yeah. That's about, should be about right, 0.01 molar. So most of your body is very diluted.
You have to know a lot about polarity.
Not a lot of it, no. Alright, so here's what I want you to concentrate on. We're not going to have time to talk about pH, so we're going to pass on pH. So here's what you got to do. Here's what you need to know.
Instead of those things you used to call it. They were basically like 3 pieces of paper in one bind that was about the size of that.
What's 50
He had 20 pages.
Really?
Well, some have different ones.
I was gonna be really snuggy today.
I think God made you not do that for me.
It's okay. It's pajama day for me every day.
I wish I could go see something. But instead I wear like shorts. Even they're in withdrawal, it's just all shorts.
I wear like, I always wear like plus
I like oh my gosh, after you should
yeah, you have to wear like really soft pants.
and then I know it's so but if you put oils on it or if you put like baby oil on it, if you put baby oil, oh my gosh, your legs are so A1.
Every time I change my legs in my friend's house, I always be like, feel my legs. It's all
Like me and my friends said Snapchat. You know that
it's like, I'm proud of my legs.
exactly. I make my mom first and she walks in the house and she's like, wow. It's so smooth.
You know? I do that. It's so much better.
Oh, yeah.
Oh my gosh, guys. I do that for like various conditions. What do you call it? From House and Man.
I get like a big one.
I've used the argan oil one. Oh my god. Why are we telling this like?
But it's true, like, yeah. And ever since I started doing that, I saw it on Pinterest.
Okay, so kind of like the starter question, you need to know why something is polar. Why is water polar? It's asymmetrical and it's got electronegative atoms on one end and not the other. Let me just go through them quick and then see whether or not it answers stuff.
Calorie? No molarity what?
No molarity calculations.
So
So that's not for Miller's test?
No, I'm not going to ask you to calculate the molarity or the molar mass of some. Okay, good. That means we don't need to talk about it anymore as we run out of time here. All right. What a hydrogen bond is. Like, what is it? What is attracted to what? Why? Hydrogen is attracted to oxygen on a different atom or a different molecule, not the same molecule. You can't. One water molecule can't hydrogen bond with itself, right? And it's doing it because of the charge differences. What's adhesion? And then some examples of, like, you know, what that would cause, or what that would do. What an example, like, you know, the way it was forming the meniscus on the glass, the way it was being pulled up into the capillary tube. I'll give examples from the lab. Cohesion, what that means, and how it causes surface tension. What causes specific heat, like what the specific heat of water is, which is 1 gram. There will probably be a question where you have to calculate that, but that's, 1 gram per, 1 calorie per gram per degree. So physically, why does the temperature change slowly? Because it has to break the bonds between the atoms first before it can get them moving around and increase their temperature. The heat of evaporation is way higher than the specific heat. It takes away, 360 calories per 380 calories per gram, to evaporate it, which is why we cool off, why even being around water, why being at the beach is cooler. Right? The water evaporating is like taking heat from the air in that area. Why does ice float? Why is it important that ice floats? And then how do things dissolve? What does the hydration shell do? What does it look like? What's stuck to what? And why is that dissolving things? Why is the fact that it's holding individual molecules of the substance apart, that makes them dissolved. They're in solution now.
What about with all that stuff about the disaturates and the polysaturates and all that?
So, Mr. where are the
benefits for
Are we doing the disaturates and the polysaturates and all that?
No, we're just doing this. Okay. It said chemistry test. It's just water test. We haven't even spoken about macromolecules yet. The test tomorrow is just on this.
It's not a chapter 3?
How many
And
questions?
where will this be on Coolidge?
No, it's nothing on chapter 3 yet.
Wait, really?
No. If I wrote chemistry, I meant water. We haven't even...
I thought water.
Didn't we just have it?
Water is chapter 2.4, 2.5, whatever that is. No, this is not on proteins, amino acids, polypeptides, dehydration, synthesis, none of that.
And no pH balances will be on.
And no pH. Higher as in numerically larger number is a low pH.
Yeah, like it said.
14 is the low. 14 is a high pH, but it's not an acid. It's a base. It's very not acid. Where
It said that pure water was like at
7, right in the middle, because it goes 1 to 14, and 7 is right in the middle. So it's not acid. It's not base. It's not either. It's sitting right there on the fence. Not going one way or the other.
So one is more acidic.
1 is the most acidic. Yeah.
And why is it harder to clean up blood?
Why what?
Why is it harder to clean up blood?
Hold on.